Okay, let's go ahead and get started. Hopefully we'll be able to make it through class without fainting today. Huh? Yeah, sure. Let's go ahead and get started. Sorry it's so warm in here. Not a lot I can do about it. Okay, so I just wanted to say a couple more things about encodings from last time, and then we'll launch into Unit 4. Any questions picking up from last time? Or for any discussions that have been going on over the last couple days? Okay, so I don't want to say too much more about this, in part because I'm by no means an expert in these encodings. But just to give you a little bit more of an example and just a feel for what's going on here. So this is an example of some text that appeared in some data that we read in from some internet logs. I think it was last year or maybe 2 years ago. And it caused us some trouble, which made me then sort of look into this a little bit more. So if you do something like this, you can do that, and then R just treats this as text. But in reality, what this E7 is, this is in base 16, and the /x means treated as a base 16 or hexadecimal encoding in this Latin 1 way of encoding characters. And so if you tell R to convert that thing from Latin 1 to UTF-8, which is the standard way that R encodes all of these different kinds of characters. And last time I mentioned that UTF-8 allows one to encode something like 100,000 different characters, including presumably characters from lots and lots of different languages. So if we go ahead and run that, and then we look at this new text string that was the result of doing the conversion, you can see it actually shows us that, this sequence encodes the C with a little guy on the bottom here. Okay, and so if we recognize that this was in a form that was sort of encoded in this Latin 1, and we do the conversion, we can see what it is in a more readable way to us. If we tried to convert that original text string to ASCII, here I'm going to say what this additional argument means is if you can't figure out what to convert it to, put in 3 question marks in a row. And you'll see when it does that, indeed, it doesn't know how to interpret this in terms of ASCII characters because it's not one of the 128 ASCII characters or control codes, and so it just has to substitute in sort of a missing value in the place of that. Another thing that we could do rather than using this icon function, which is also a Unix utility. So if you had a file, you could use icon in Unix to convert files within Unix. And R just took the same name because it's doing the similar sort of operation. But another way we could do this is we could take a string that has something that's in this Latin 1 encoding and tell R that the encoding for this object is Latin 1. And once we do that, and now if we just print X out to the screen, it is indeed able to recognize the C with. Does anybody know what this thing is called by any chance? Huh?
Does that say Cedille?
Okay, Cedille. Okay. So we can sort of get a feel for what's going on here, and so you could even play around some with this. Part of what I'm going to say as we launch into Unit 4 is the idea of just playing with code and sort of seeing what happens to really explore what's going on. So I just started playing around with this, saying, if I know these things are in base 16, I can use any digit from 0 to 9 and any letter from A to F. Let me just see if these, if some set of these encodes anything particularly interesting. And once I do that, and then print out, I have to again say what the encoding is. But once I do that and then print out the X, we can see, it turns out it looks like Latin 1 can encode an upside down exclamation point, presumably for Spanish, and this cent symbol, and the British pound symbol, and an enye, and all of these other potentially useful characters that you might want to work with. And that happens in this data set ips.r data. So if you wanted to look at this a little bit more, you could run through this demonstration code and see an actual demonstration of a case from last year or 2 years ago when we ran into this and we had to do this conversion for a real set of data. So I think that's all I want to say about that. Are there any questions before I jump over to Unit 4? Okay, so Unit 4, as I think I mentioned in one of the announcements, is the other thing I'll say is Unit 4 and Unit 6, or it's a little bit hard to know what my reasoning was in terms of what went in Unit 4 and what went in Unit 6. They're both about doing stuff in R and programming in R and some of the concepts that are used, some of the concepts that are important in knowing how R operates and how it treats code that you give it. Unit 4 is supposed to be more sort of using R as sort of a user, and 6 is more about programming, but the distinctions sort of blur together. And in terms of Unit 4, I'm really not going to say too much about the first 6 sections or so, as I mentioned in the announcement. What I'm going to do, we'll see how this goes, I think it'll be a useful way of doing this, is what I'd like to do is just hit a few examples of sort of, we can think of them as sort of puzzles, of sort of seeing how R operates by virtue of looking at a few of these concrete examples. And then I'll leave the rest of it for you guys to look at on your own. And then on Friday, we'll do a lot of stuff with scoping and frames, so we'll really look intensively at Section 7 of Unit 4. And then that'll probably go into Monday, and then Monday, Wednesday, maybe into Friday of next week, we'll do a lot with string processing, text processing, and regular expressions within R. So that's sort of the game plan here. Okay, so the idea here is we're going to look at a few of these examples. We're going to try and play around with some different ways of using the code and see if we can discern sort of what are the rules by which R is operating. And part of my goal with this is to get you guys in the mode of, if you see something unexpected, don't treat it as sort of an unsolvable mystery. Like, computers are deterministic, right? And they operate by a series of rules. And so we should be able to figure out, either by reading the manual or by actually probing the system and trying different things, we should be able to figure out what the rules are and why we get the behavior that we observe, even though in some cases it is indeed puzzling. Why, it can indeed be puzzling why we get that behavior. So actually, one example of this goes back to when we're in Unix, and somebody asked the question of why can't we put spaces around the equal sign in Unix? So we were trying to define a variable. And if we did something like this, myvar equals 7, we saw that didn't work, and it said myvar not found. And one of you posted a really useful note on Piazza that explained what was going on here. But if we look at this error message and we think about what's going on here, and we think about what other kinds of Unix commands might we run, they're all of the form a command followed by a space followed by some input arguments or some input flags. And so if you think about what the rules are by which the shell is operating, what's going on here? An input command followed by a space followed by presumably some sort of arguments or flags. But in this case, myvar is not any sort of command that we could run. And so it says, oh, I'm not recognizing the command myvar because it's expecting something that's in this sort of form when the first thing is the command, and there is no command of that sort. Whereas however the shell interpreter is set up, if you do this, it's going along, when this gets sent to the shell, it's going along, it's parsing these characters, and then it's trying to interpret what to do with them to carry out the operation that you asked for. And presumably the rules are set up so that it knows when it hits an equal sign to say, oh, the thing on the left-hand side of the equal sign must be a variable name, the thing on the right-hand side of the equal sign must be the thing that I'm supposed to assign into that variable. That's not to say that we couldn't have written, whoever was writing the shell interpreter couldn't have written it so that it would handle this. It just doesn't happen to have been written in that way. Okay, so let's switch back to R. Actually, I think I'm going to go to the PDF here. So again, there's a whole bunch of stuff about interacting with the operating system from R, and if you want to run a Unix command from within R, you can use the system function and then give it whatever shell command you want to give it in quotes. And you can internalize the results back into R with this intern equals true. And there's a bunch of other functions for sort of interacting with the operating system that may come in handy in various cases that I'm not going to go over in detail. There's also various functions that allow you to get information either about what kind of system are you running on, so that's the sys.info, or some of the options that are set up for how R operates, and also you can get information on your particular R session, what version of R you're running, what platform you're running on, what are the packages that are attached. All of these things can be useful for sort of knowing what's the state in which you are when you're carrying out things. And particularly if you're submitting a help request online to a mailing list, it's good to provide information of this sort so other people can know what the state of your system is. Okay, and then the last thing I was going to say here along those lines is we can also, one nice thing about R is you can have R, you can have a script that's not, instead of having it be bash code, you can have the script be R code and just execute it from the command line in Unix. And basically you just create your R code file, and then if you remember, when we're making a bash shell script, at the top we put the #bang/bin bash to tell it to interpret the code as bash code. We can do the same thing with R, except that with R code, except then we put in this #bang and then user bin R script, and that tells the operating system to interpret the code in the file as R code that's going to be executed by the R interpreter. And again, we'll have to make the function, we'll have to make the file executable with changemod, and then we could just run it from the command line. And there are also ways to basically pass arguments in. So the ultimate goal of this would be to be able to do something like my R file 7 blah 63.7, whatever, to be able to execute this code and have these 3 items be read in as 3 arguments that get placed into R objects in R that you could then use to control the flow of your R code. Okay. So there's not all that much to it. It should be pretty straightforward if you just look at the notes and just play around with it yourself. So I think I won't bother to do that example in detail. Are there any questions about that, though? Okay, let's say a little bit about packages. We already know that we can load packages in with the library command. If you want to get help on a package, we can do it by saying library and then help and then the name of the package that we're interested in. So if I were interested in the fields package, it'll give it an overview of what the package is and what the various objects in the package are. So these might be data sets, or in general they're mostly going to be functions that are in the package. So that can be useful, because otherwise if somebody hands you a package and says, hey, go use this, it sometimes can be hard to know where to start and what to do with that package. I seem to have gotten myself into a state I cannot get out of. Oh, there we go. Okay. Let's see here. Okay, so that will give you sort of an overview there. And then another thing that's useful to know about in terms of packages is packages can be installed in different places on your system. And the reason this function that you load a package in is called library instead of like load package or something like that is the library refers to the location on the file system where packages are stored. So it's sort of a convoluted way of naming things. But sometimes there are these R functions that start with dots that are basically sort of internal functions that are not in general meant for users to use. But since we're doing a whole class on statistical computing, you guys are now qualified to use these very fancy functions. And this is actually a bad example because there's only one location of packages here. So I'm actually gonna try this just on Radagast, one of the SCF machines. Just to give a little bit more of an interesting example. So here what this says is packages might be stored within a directory in my home directory, or they might be stored in some of these paths that are sort of more locations that are sort of more system level locations. So part of the reason that I'm mentioning this is there can be cases when you might have a package, say that I was talking about that fields package, or let's take that XML package we used for loading in HTML the other day. Maybe you've installed the XML package and it's gotten installed here, but there's also an XML package that's been installed by somebody else, say one of the systems administrators, somewhere else in here. And so you could actually have multiple versions of the same package installed on your system. And those might potentially be different versions, and there could be some confusion as a result of that. So it's good to sort of just know that this can happen. And if we use this search paths command, this will basically show us where R is looking for functions in packages that are loaded into your particular R session. So, and it basically gives an order of precedence. First, it's going to look in the global environment, which is just your working environment that you would see if you just type ls or look on the right-hand side of the of the RStudio session. But then this actually says, you know what, all of these packages are loaded in, and in fact, here are the paths on the file system that tell you exactly where I'm getting that package from. So this tells you without any ambiguity the fact that it's getting the stats package from this particular location. It's getting, in this case, there's another sort of system level package called SCF that it's getting from this location that's a different place on the file system. And when R goes to look for a function, it's basically going to first look here, and then it's going to sort of march its way through here, continuing to look for that function until it gets to the end. And if it hasn't found it then it will return an error back saying, yeah, I can't find the function that you're looking for. Okay, so any questions or comments about that? Okay, the other thing that you can also get at something that looks very similar to what I just did with search paths if you just type search, and that will show you basically the same thing in a slightly different format. It'll say, first I'm looking in the global environment, then I'm looking in the fields package, then I'm looking in maps and whatnot. But it basically shows it to you without the directory structure of where on the file system it's sitting. And so part of what's going on here is this idea of having workspaces or namespaces, which is a principle that's used in other languages as well. And the idea is we don't want to have all of the thousands of functions that might be available to us be printed out if we type ls at the prompt, because it basically makes things sort of overwhelming to sort of see everything possible that's available to you. So the idea is to sort of divide things up into little chunks where each chunk or namespace corresponds to a given package. And then R will go look in those different namespaces when it needs to go find a function. But they're sort of all collected together in these little discrete modules as a way of sort of keeping things clean and tidy. Yeah.
I'm just wondering how R search for those packages. Was the order, we can start from the global environment and then what's next?
Yeah, so this is the order. And as you load packages in, those will basically get inserted right below global environment. And so that's why fields comes before some of these more sort of base level packages, because I loaded in fields as my own user option. Yeah, so it's sort of like a stack of things. So anytime I say, oh, if I call library and then a package, it's going to basically end up on the top, just below the global environments, and then there'll be the ones that I loaded in, and then there'll be the system level ones, and that'll be the order in which R goes to look for any function that I specify, or any for that matter, any object that I specify. But we can use ls not just with the global environment, not just with your own working environment and workspace. We can use it with any of the packages as well. So as an example of that, I can say, tell me what's in the 8th position on the search path. That actually is going to turn out to correspond to the stats package in this case. That might not quite be true. So I think because I loaded the fields package, that's actually probably going to be the 9th one, because the fields one got inserted above it. So now if I do this, oh, that didn't work either. That's interesting. Oh, that's because 9 is apparently this auto loads thing, on which I'm not sure what that is. So somehow or another on this particular, at this particular stage of my operating in this particular section of R, I would need to say number 3, because that should be that's the 3rd position here, and hopefully that will work. And then if instead I specify the environment to look in or the namespace to look in with by saying, giving it the name of the package here in quotes with this particular syntax, I should see the same thing. So those are the first 5 objects that are in the stats package. And if we didn't do the 1 through 5, we would see all of the different objects that are in the namespace of the stats package, and they're the sort of things that you would expect. They're all the things you need to do statistics, sort of basic statistics. So there's all the stuff about linear models and quantile plots and functions and all those sorts of things are all wrapped up and packaged up in this namespace that's the namespace for the stats package. Okay, I think that's all I want to say about that. Any questions at this point? Yeah, and you're Guang?
Yeah. So are you pretty screwed if like there's 2 different packages use the same function names and you didn't actually know that there are 2 of them?
Yeah, so that can cause problems, and I think we might have actually seen that already, but it might have sort of gone by without us really remarking on it. I think when I loaded fields in here, did I? Oh, I didn't. Did I load fields in here? I must have, because it's on the search path. But I don't know where I did that. Well, let me just do that in a separate R session out here. Okay, so if I do library of fields here, you'll notice something here. It says the following objects are masked from package base, and it says backsolve and forward solve. So in the base package, there are these functions for doing linear algebra, for doing backward solve and forward solve that we'll talk about in gory detail in a couple months, that are in the base package that handle dense matrices and backsolves and forward solves with dense matrices, so solving systems of linear equations. But it turns out these functions are also named functions with those names are also in the spam package, which deals with sparse matrices. And whoever wrote the spam package used the same names for the functions that are in the base as in the base package. And so if we call backsolve, what's probably going to happen, there's maybe a little bit more complexity behind the scenes that I think I don't want to get into at the moment, but probably what would happen is that backsolve would basically mask the one in the base package. There's a little bit more going on here because I think there's some S3 object-oriented dispatching going on that we'll talk about in a few weeks. But in the simplest case, that's what would happen in here. And if you just called backsolve, it would use the one from the spam package because that's higher up in precedence than the base package.
So it does give you a warning. So it's
Yeah, in this case, it does give you a warning. But I could do something like this. I'll do it with the assignment operator. And now I could say backsolve, and it says, oh, that's the number 3. Right? But it's not so bad because it turns out if I say, this is not going to quite work. If I say let's say x equals 5 or 45, and then I say backsolve of x. This is wrong because I need to give more arguments than just x to do a backsolve. But if you bear with me, despite that fact, it actually does know to go look for the backsolve function in this case, because it's seeing that you're treating it as a function instead of just an object here, instead of just a variable. And so because you put it in this sort of syntax, it knows, oh, don't get the one that has the 3 in it, go look for a function of this name. And the fact that it's not looking for that it gets the base one instead of the spam one has to do with a bunch of object-oriented stuff that I don't want to go into yet.
So what if I write a function with the same name, it's going to override or mask?
Yeah, it's going to mask it. It's not going to overwrite it. It's still going to be the other one is still going to be sitting in the namespace of the package that it was originally in, but it's potentially going to be masked from your use. Yeah.
How to release the previous one?
Well, you could remove the one if you create a new one. You could remove it, and that'll sort of make it obvious to you. Or you can do something like, even if I had said backsolve, is a silly function that just returns whatever you put into it. You can still get at the original one by saying look in the namespace, in the base namespace for the backsolve, and that's the backsolve I want to use. So you could still do it with this double colon operator, which is basically resolving what namespace to look in. Okay. So the next thing I'm going to do is launch into a couple of these sort of little puzzles and see what you guys can make of this. So here's an example where I'm going to use the equal sign to do assignment. So this is perfectly valid in R. You can either use the equal sign or the actual assignment operator, and that will work. But here's a case where if system.time is a function that will try and tell you how much time it takes to run an operation or carry out an R expression. And if I try and do that here, what it says is, oh, there's an unused argument out when I try and call system.time. But if instead I do it like this and I use the actual assignment operator here, what you'll see is it'll actually give me back the time it took to carry out this operation of generating 10,000 random numbers. So what's going on here is R is recognizing this whole thing as an R expression that happens to do an assignment, but it's recognizing it as an R expression, and it's timing how long that expression takes to carry out. But let's think about what is happening here. Think about system.time as being a function And then we have this syntax in here. What do you think system.time is actually trying to do? I guess I've already sort of maybe given it away a little bit here. But think about what this looks like just from the perspective of having a function and then giving it some stuff in parentheses. Yeah. And what's your name?
Chris.
Chris.
It's treating it as an assignment to the parameter. So you can instead put braces around the expression and kind of make a closure, I guess, and it would then work.
Yeah, so this is saying, okay, this is a function. This looks like an argument name. And this looks like saying, oh, pass this in as this argument. But if we think about whatever the arguments are, whatever the names of the arguments are for system.time, system.time doesn't have any arguments that are named out. But it looks like we're trying to tell it that there's an argument named out. So that's indeed why we get this expression here. It says unused argument. Well, it's unused because it wasn't expecting this argument out, and therefore it says I'm not going to make use of it. I sort of don't know what to do with that argument because it's not an argument I was expecting, and therefore it errors out. So that's another one of these examples, like I was saying with the bash shell script, of why the variables of why we can't put spaces in, of where if you try and think about this from the perspective of a computer, of like carrying out a set of rules, we can interpret what these error messages mean and see sort of what our interpreter is trying to do when it sees code like this and why it gives back the error messages that it does in the cases where we get an error, or sometimes we'll just get an unexpected result. All right, so what I want you guys to do now is let's look at the mean function. So this is what the mean function looks like. It's a function that takes some argument called x and potentially some additional arguments, and then it does some other stuff that turns out it's actually going and calling some. Eventually, it's calling some C code here, but there's some object-oriented stuff here that I don't want to get into. But if we focus on this of what it's expecting as input arguments, what I want you to do is think about what this code does and why it either gives an error or doesn't give an error in the cases that it does. So I've got sort of 4 different cases here, and I'll go ahead and run them, and we'll see that it looks like 3 of them succeeded in the sense of they ran without an error, and 1 of them failed with an error. So take a couple minutes. Actually, why don't you pair up, find a person or potentially 2 people next to you. Try and pair up and see what you think each of these 4 things is doing and why it is that R is treating them in that particular way. And then we'll reconvene and see what we can make of this. All right, let's reconvene and see what people think here. Okay, and let's remind ourselves of what the mean function looks like. So the mean function is expecting an argument named x, right? Okay, so you'll notice in the comment here I said, oh, this is the usual way to pass an argument to a function. So this shouldn't look unusual to anybody. This is just saying, oh, it's expecting an x. We're going to give it an x, which happens to be a vector of the values 3 and 7. So then what happens? In the function, the x gets assigned in the body of in the environment of the function, in the frame of the function, as the function's executing. X gets assigned to be 3 and 7, and it goes and does something with x to compute the mean. Right, so that's sort of the usual thing. Okay. What's different about this? And can anybody want to venture a guess about what happens here that's different than what I just described? And why it actually completes and carries out and doesn't give an error message back?
You're essentially creating x. You're sort of overriding x, like the original x, aren't you, in this case? You have your function that's expecting x, but here you're sort of saying, okay, x is equal, so I'm reassigning it.
Okay, so yeah, if we think about this, and remember we talked about this idea of sort of this is a valid R expression, right? Think about another way to think about this is what happens when I do. What's a good example? Maybe even just this is a good example. This is an R function called C. It takes as inputs the value 3 and the value 7. When R sees this, it works from the inside out and evaluates. Basically, it's evaluating this inside thing, and then that's getting passed in as the argument to the mean function. So it's carrying out this operation, and then it's carrying out the operation here. And I could have another function wrapped around here, and it's just the sequence sort of nested calls, right? Well, there's nothing really all that different going on here, and as Brianna's pointing out, this operation is going on, this assignment is going on. So we've already actually run all 4 of these. So if I'm about to type x here, anyone want to guess? And maybe Brianna wants to weigh in on what I'm going to see as the value of x in my workspace here. It's going to be 3 and 7, and it's not going to be 0 because this got carried out, and the fact that I've done this as the argument to this gets carried out in basically the place from which it's being called. And so this assignment gets carried out in the global workspace, and it is indeed a 3 and a 7. Okay. So then, hold on one second. Then if I run this and I look at out, it is indeed 5. So it's still carrying out the mean calculation, right? So why does that work? Why does it work even though I didn't say x equals? So after I've done this assignment, what then has to happen in order for something to go into the mean function? I may have phrased that in a confusing way. Yeah, Chris?
It needs to return the result of the assignment.
Yeah, so this expression, after carrying out this R code, this expression itself actually has to have a return value. It assigned into the x, but then the result of the actual assignment has to be basically being printed sort of to standard output in some sense, if we were thinking in sort of Unix terms. And if we think about what goes on when I can do this in R. The reason this works is R is basically working, in this case, from right to left. This is going to assign 3 and 7 to x. The output of that assignment function, assignment is actually just another function. It's a weird looking one, but it's just another function. The result of running the assignment function is it also outputs basically just to the workspace whatever happened to be assigned to the variable. So the result of this is not only putting 3 and 7 in x, it's also basically printing out 3 and 7, except it sort of happens invisibly, so you don't actually see it printed on the screen. But the fact that the result of this is just 3 and 7, it also gets passed along and then gets passed into A. It gets assigned into A as well. And so that's basically what's going on here is 3 and 7 are getting assigned into x, but the result of this expression is also just 3 and 7 on its own, and that's getting passed into the mean function. And of course, since the first argument of the mean function is x, it's just getting assigned in as the x, even though we never named the fact that the input is the x argument. It's just being assigned by position as the first argument. Okay, so I think I may have skipped over a question a few minutes ago. Was there still a question? Yeah, Jan.
So if we just run x equal, then when we output the x value, will still be 0.
So say if
we just do
if we do this one?
Right.
Okay, so let's reset x and then do this. That's what you want me to do? Is that okay? Yeah. So now, as you say, this. Oops. Right. I don't want to do that too. Okay. All right. So now we do this. Now we look at x. Yeah, it's still 0 because there was no assignment going on in your workspace. Yeah. Okay. So now what happens here? We saw that was an error, right? So somebody want to explain to me what's going on here? Yep, Kelly.
That's the same error that you had before in that mean is literally expecting x and you're telling me that I'm going to pass the y.
Yeah, so I'm passing in an argument called y. This would actually be allowable because mean is expecting with the 3 dots. Mean could actually take multiple arguments, in particular some that don't necessarily have names to them. But the problem is I'm saying pass in a y, pass in something called y, but I'm never saying pass in an x, and it's expecting an x. It needs an x. So it says there's no x, it's missing, and there's no default value for it, and therefore I'm gonna error out because of that. But if I had done mean of 3y equals 7, that would have. That's interesting. That's what happens when you experiment a little bit too much and don't know what the result is going to be. So.
I mean, it's just ignoring y, right?
Huh? Yeah, I mean, in this case, it's just ignoring y. So we'd have to go in and figure out what the ... is doing further on down in the mean function. Yeah, because I guess mean is expecting a single argument which could be a vector or a matrix, and it's going to take the mean of all the elements of the vector or matrix. So it's not actually going to do any mean calculations with whatever the ... is. That's getting passed along, I think, as sort of it's probably if you include na.rm to remove NAs, that gets passed along, and some additional sort of toggle switch kind of arguments. Okay, so then what happens here? So somebody want to lead me through what's going to happen here and why this doesn't give an error? Yeah, Julie?
It's creating the assignment to y and
Yep.
the outside
Yeah, so it's doing the assignment. It's going to overwrite the y in our workspace. But then the 3 and 7 are the result of the assignment. Those are going to get passed along and passed into the mean. But I'm never actually saying the argument is named y here. This is not naming the argument to the mean function. It's just saying assign into y, and then the result of that gets passed in, and it's getting passed in as the x argument to the mean function. So all of this, except for the one that briefly hung me up here, all of this is interpretable in terms of what the error messages say if we can sort of interpret what the rules are by which R is doing this processing. And some of that could come potentially by looking at a manual, but a lot of it, in my case, and I think in most people's cases, comes by saying, hey, I'm curious what happens here. I'm curious why that happened. Let me try a few different cases and see if I can tease out what the rules are by which it's doing the interpreting. Okay. Similar sorts of things go on if you use an apply function, where if you use an equals or an assignment here, and you could ferret out what goes on there as a little exercise to make sure that you're understanding this if you looked at that. Okay, so I want to say a little bit more about types and classes and coercion in R. So one of the things to recognize, hopefully this is still up on my screen here. Yeah, so this is from the Adler book, which is in the syllabus as one of the references for R. So there are two functions in R that will tell you something about what kind of object you're working with. One of them is type of, and one of them is class. And type of really gets at sort of the fundamental, how R is fundamentally treating the object, basically at the C level. So R is basically a program that is basically carrying out all its calculations in C. That's from, must be from a Google chat I was doing. The party's over. So if you ask type of and then give it an object in R, it's basically going to return one of these sort of fundamental types that are listed out in this table in the Adler book in chapter 7. And these basically have to do with how does R store information basically as an object in C. And so a lot of things are stored as different kinds of vectors. There are these compound objects like lists and these other things that are sort of more complicated. There are objects that have to do with the actual syntax of the language that we'll see, I guess, in Unit 6 some. But these basically are sort of building blocks. And then if you instead use the function class, this has more to do with sort of what kind of object is it at the level that a user would generally need to know. There's one piece of half-inch long chalk in this entire room. So if we say class, it's going to return back sort of what kind of object is it at a sort of higher level, a sort of user perspective level. And this also gets into object-oriented programming, that if we start creating different classes that objects are instantiations of, class will tell us what kind of object is it in an object-oriented framework, and we'll see more about that as well. But the thing about R, as you guys know, is that you don't have to tell R what kind of object it is before you just start using the object and assigning to the object. So that's like many interpreted languages, but unlike something like C or Fortran or C++, where you have to say in advance what kind of object is any given variable. So the result of doing that is that can be very handy, because you don't need to go along and say, okay, x is going to be an integer and y is going to be a character string, and then I'm going to use x and y. You can just say x is 5 and y is Sam, and then you can just start using them. But the result of that is also that R often ends up doing a bunch of coercion behind the scenes. So if you try and run a function on an object that is not of the type that it's expecting to be the input to the function, it may, instead of sending you an error message, it may basically coerce or convert that object behind the scenes to another kind of object. And so the result of that can often be, that's often helpful, but it can also be a bit troublesome at times. So here's an example of that. Suppose that we create a vector of 5 numbers, and so there's nothing wrong with that. Those are 5 random numbers. But now I assign in to the third element the string hat. Right? So you can think about what could happen here. You can think about, if I'm designing this language, what are the different things that could happen when I do this? So what are some of the things that you think could happen here? So it could certainly return, this could potentially be an error, right? You could write the language such that this would return error if you try and insert a string in the middle of a bunch of numbers. Right? What other things could happen? Okay, so it could try and convert everything to something of a common type. So it could try and convert hat into a number, right? That might be kind of hard. It's still not really clear what hat would be as a number. But the other way it could do it, if it's trying to go the other direction, it could try and convert all of the numbers into strings, right? So we could see if that's actually what happens. That should actually be what happens here. So you'll notice it took all those actual numbers and then turned them into strings, which we can see because there are quotes wrapped around them now. In addition, there's hat. So you might or might not like the fact that this is what R does, but when the developers of the language were devising the language, they decided that a lot of this kind of coercion would happen behind the scenes. And sometimes it can trip us up in ways that we'll see. Here's another example where I'm going to use as indices the numbers 1, and I'm going to use 2.73 as an index, which seems like a crazy thing to use as an index, but it seems like it does some sort of truncation. And since the second element of this is a 2, what it must be doing is taking the 2.73 and taking the floor function and applying it to the 2.73. Okay, so here's a little problem to think about, and we'll come back to this next time. I'm going to create a data frame that has one column that's of strings, one column that's a second column of numbers, and another column of numbers. And if I look at that data frame, indeed, that's a perfectly legitimate data frame. It has the strings. It's got the numbers. If I say sapply to data frame and then the class, actually, it looks like it converted the strings to a factor variable, but in any event, it's got factors and numeric values. And so I might think, if I were coming along and thinking about trying to sum the second and third columns by row, I might think about using an apply function and saying, oh, I want to operate by row. And what I want to do is I want to pull out the second and the third elements of each of the rows. So here's an anonymous function that I'm defining on the fly, right? And so when I do an apply, x at any moment in doing the apply should be a given row of this object. And so then this should take the second element of the given row and the third element of the row and add them together. So that should work, right? Because the second element and the third element are both numbers. I should be able to add them together. But if I do this, it says, oh, wait a minute, I'm trying to add x2 and x3, and that's a non-numeric argument to a binary operator. Well, that seems kind of crazy, because I know that I just looked, and I figured out that those things were numeric. Right? So here's another puzzle. Like, what's going on behind the scenes that makes these two facts be consistent with each other when it seems like these things are inconsistent? So I will close with that puzzle. I know you guys have the problem set due on Friday, so I won't assign this as something you have to do for class on Friday. But if you do have a few minutes, think about this, and you might look at the code in the apply function and see if you can figure out what might be going on that's causing us to get that particular error message. So let's quit for today.